Hello everyone, my name is Marko. I'm a software security architect at NVIDIA, and I'm really happy to be here in person to tell you our story about systematically securing our RISC-V stack. This is actually a story of rebuilding our security foundation for all our GPU-based products using RISC-V. NVIDIA builds platforms and machines that create and process data that is critical to our customers to protect. And what we're witnessing is that security is becoming more and more important in pretty much every vertical our products are targeting. In a different way, with different priorities, sure, but still, security is now, it's safe to say that security is now very important pretty much everywhere. The core hardware we build and most of the core software is leveraged across all our products. And the security of all our GPU-based products has its foundation in embedded controllers. And today I'm going to talk about how we are re-architecting this secure foundation with RISC-V at its core. There are, of course, many different types of security vulnerabilities and different types of attacks. But first, our GPUs are deployed everywhere. And while complexity is the greatest enemy of security, products are demanding more and more of both on ever more aggressive schedules. And at the same time, NVIDIA demands flexible hardware and different products from the same silicon. New features and long-lived products with ongoing development are pushing more complexity into microcontrollers, which actually can lead to very expensive security incidents we had already, unfortunately, had already chance to experience. And these incidents affect our customers also. As I said, there are many different types of security vulnerabilities and different types of attacks, from pure software ones like memory corruptions or hybrid like spectral meltdown that leverage both hardware and software flaws, to the pure hardware bugs and physical attacks. They are more or less critical and important depending on the vertical, but what we are noticing is that attacker trends are shifting lower, targeting our most critical firmware. And firmware is omnipresent in pretty much every product. That critical firmware running on embedded GPU controllers presents the foundation for all our GPU products. And what this meant for more than 10 years now is that we relied on our proprietary Falcon architecture, which was very successful but couldn't meet these new growing security demands without much higher cost and less flexibility at the same time. That's why we are replacing these legacy Falcon cores processors with new NVRISCV cores. We are building this new security architecture around NVRISCV. Since we all know what RISC-V is here, I'll switch over to NVRISCV, which is just NVIDIA's implementation of the RISC-V instruction set architecture. And Peregrine engine would be NVRISCV CPU with devices such as accelerators for cryptographic functions and DMA devices. So to build a secure foundation, a holistic view across both software and hardware is needed. And we at NVIDIA are perfectly positioned to leverage hardware-software co-design, which at high level would mean to push policies in software while designing fine-grained mechanisms into hardware to allow flexibility. Our core policy management is layered and split between Bootrom and separation kernel software components that together with the Peregrine hardware form this secure foundation. This architecture also offers multiple isolated execution environments we call partitions, and this is where actual applications and feature-specific functionalities would run. This is how we are able to isolate and contain complexity in software while following principle of least privilege and defensive depth. This also allows us to focus both offensive and defensive security investments across multiple dimensions of this foundation. The key idea was to design and implement critical security functionality once and then leverage. So one of the main goals we had from the beginning was to be able to stop adding new physical separate cores whenever we needed security and isolation. And idea behind multiple independent levels of security and safety is about 40 years old. But we just felt that several key pieces are now just mature enough so that we can achieve this efficiently without compromise in security. The Bootrom would be immutable software component that serves that is embedded into hardware and serves as a root of trust. And separation kernel is the first mutable code verified by the Bootrom that runs on the core. It is the component that is responsible for creating and managing these isolated execution environments we call partitions. The isolation between these partitions is as strong as the hardware that's enforcing it, of course, but also as the software that is managing these primitives. That's why we chose to implement Bootrom and separation kernel in Spark, which offers formal guarantees about the correctness of the implementation. And I'll talk more about it later. The root partition here on this diagram just signifies how we are able to keep separation kernel as simple as possible and extend its functionalities with what you would otherwise consider separation kernel's functionality and push that into a less privileged execution environment to a root partition. So that would be an optional partition that has some specific, use case specific or capabilities, and that would also depend on type of the core. The key design principle for this design was just to keep everything as simple as possible. We're now diving a bit deeper into separation kernel, which is that software component that presents foundation for running mixed criticality applications on a single NVRISC-V core. And it does that by configuring hardware access controls that control what hardware is exposed to partitions. So that partition, when they get access to the core, they will talk to the hardware directly. So separation kernel does not provide any abstractions to the hardware. The execution would start with Bootrom that configures the hardware per how it is defined in the manifest. And manifest is signed static configuration set that tells Bootrom how to configure hardware and limit what is possible on the core once Bootrom is done. So it creates an environment for the separation kernel for the first mutable code that comes next. And partition policies are also signed static configuration sets that then separation kernel would use to further configure hardware and create these execution environments, that is partitions where actual applications will run. Whenever a different partition should become active, separation kernel would just use corresponding partition policy to reconfigure the hardware before it transfers the execution to it. Therefore, we can say that these partitions are or can be NVRISC-V's trusted execution environments. And now zooming into the Peregrine hardware that follows a layered access control scheme. The NVRISC-V processor supports 3 privilege modes: machine mode, supervisor mode, and user mode, with machine mode, of course, being the highest privilege one. And there are several access control hardware units that control physical memory access, access to devices, debug profiling control, access to secret hardware keys. And those units are only configurable by highest privilege software that is running in machine mode. And in our case, those are only Bootrom and separation kernel. We have several countermeasures against physical attacks, and I'll talk more about that later. So out of reset and before any software runs on the core, the Peregrine would be in a lockdown state. And there are default set of policies that are embedded into hardware that will enforce so that Bootrom is the first to execute. So the goal is the first instruction integrity, so the hardware is in well-defined deterministic state while Bootrom is running. The Bootrom's primary role would be to fetch both manifest and first mutable code, perform signature verification, optional decryption, and then set up the execution environment per how it is defined in the manifest. Before it transfers execution to the FMC, Bootrom should clean up after itself, which is actually a very important step as lack of such a cleanup could lead to security issues. Also, once Bootrom transfers execution to FMC, it can never be re-entered. And when separation kernel starts executing, the first it will verify that the hardware is configured in such a way that separation kernel's code and data are protected, or it will configure the hardware to be so. And then it will continue, as I said, to create these execution environments per partition policies. And finally, the applications, the feature-specific functionalities will run within partitions, and they can further choose to isolate user mode tasks using the NVIDIA's memory protection unit that also implements address translation scheme. Now, the important thing to note here is that since we employ formal methods on both hardware and software side, applications, we have formal guarantees that applications cannot escape their partition boundaries, and that is always enforced by hardware with no runtime overhead. Given the Peregrine's and RISC-V's flexible architecture, we can build many different partition configurations. In order to keep things as simple as possible, by default, there's no temporal isolation between partitions. So the scheduling is cooperative, which means that partition, if or when it chooses to switch to another partition, it will do so by calling the switch to SBI explicitly. But given all the interrupts and exceptions by default are delegated to partitions except the timer interrupt, which actually means that you can have a separate scheduling partition built on top separation kernel that can do whatever scheduling you want to have. Or you can have a model with runtime shared OS that can, among other things, also be responsible for scheduling, but partitions data and their capabilities would not be shared. And our most common use case would be where we have separate partitions that have exclusive access to certain hardware units and perform some security critical operation. Now let's switch to software. All software can have vulnerabilities, of course, especially now since software complexity is increasing as well as its criticality. And what we've noticed in our predominantly C++ code bases is that we are very much aligned with the industry in terms of what types of issues we tend to introduce in these code bases. And the below two charts are just from our internal incident response reports that actually confirm just that. There are very, very good techniques that are getting better every day we can use to find issues as early as possible and fix them, of course. And those are very good, as I said, but they have their own limitations and they have one thing in common. That is, all these techniques can just point to you that you might have an issue somewhere in your code. They can never assure you or give you assurance or guarantee that you are free of certain types of problems. Manual reviews and audits are good. We should never stop doing that, but that just doesn't scale. And also, humans tend to get tired, especially when they have a lot of things to review. Automation is desired, of course. It improves efficiency, reduces cost. But again, with security automation, you're still bounded within the effectiveness of the underlying tools. Therefore, for our most critical software, what we wanted is to be able to eliminate whole classes of vulnerabilities and have guarantees those will never happen. And what we believe is the way to do that is to use Spark. And Spark is a programming language based on Ada and set of analysis tools. It is statically provable, meaning that you can prove the dynamic checks you have in your code cannot ever fail. It has a very strong type system, supports contract-based programming, and has one very useful verification feature called ghost code. It has full set of analysis tools, as I said, but for this story, the most important one would be the prover, as we call it, which you use to actually prove the correctness of your implementation. And of course, there is a RISC-V compiler. So given it supports formal verification, it is suitable for safety, security, critical applications, and it has been used for decades in industries where security and safety are very critical. The language is mature, and there is a broad ecosystem and commercial support, and NVIDIA partnered with Ada Core, and they've been very helpful in the adoption process. But also there is an open source presence as well, so we can keep move forward even in the absence of a major vendor. Again, for our most critical software components, we wanted to put more emphasis on guarantees, on provability over testing. And one, maybe the best or most obvious benefit of using Spark is the ability to prove absence of runtime errors. This means that you can be certain that your Spark code won't raise any runtime exceptions on any input or on any path. And how is that possible? So a few years ago, I saw a talk on safety critical software, and a great talk, and they had a very nice visual way of comparing C and Ada Spark languages that should help understanding how Spark makes this possible. So in general, on a given machine, you'd have a machine state set, which is all the possible states of machine, all the possible combinations of memory and registers. And then you'd have correct states. Those would be states attained only by correct execution of your program. The boundary should be clear, as you should know what you want to build, and of course it has to be a subset of the machine state set. And then we have language states, which are the states allowed by language rules. And the boundary here is not really clear, as language specifications tend to have undefined behavior. So this is where we see high-level difference between C being the most powerful low-level programming language that tends to extend its machine state set that it can attain, and Ada being stricter, allows more correct execution. And then we have Spark, which is a very strict subset of Ada language with no ambiguities and no undefined behavior, with formally verifiable specification. And this is how it allows you to formally specify only the correct states of execution of your program, and then let the tool, the prover, prove that your code actually conforms to that formal specification that you put up front. What is great is that you don't need to learn a new annotation language or anything like that. You'd use the same syntax, same Spark language for both defining the specification and for implementation. And that is very powerful. One example would be you don't need to fuzz indefinitely your interfaces in order to find some odd inputs that you didn't sanitize. The prover will actually give you very nice counterexamples, what you missed that you show. So you keep doing that until the prover is happy, and then you know that your implementation conforms to whatever specification you put. Of course, it's very likely that you won't be able to do everything you want with 100% Spark code, so you can have these escapes, as I call them, and make calls into C, C++, Ada, assembly, or whatever. Those parts won't be covered by the prover, but then we should put runtime checks around these calls and/or even manually review them. So if we keep these escapes to a minimum, number of these escapes to a minimum, it is manageable even for manual reviews. The absence of runtime errors means that whole classes of vulnerabilities are just impossible if you use Spark. And if you recall the charts from before, from our incident response reports, we see how most, if not all, of the classes of vulnerabilities that we tend to introduce in, again, predominantly C++ code bases would be just gone if you would have used Spark. For automotive, it's great that you don't need to deal with NVRISCV violations, which is great. So by the language being more strict, the tools are more accurate, and this is how we can come to a optimal or desired responsibility split between language, tools, and engineer. Being able to identify problems early is also something that is very beneficial. And all this combined has one very, very useful side effect, and that is that it enables more efficient offensive security efforts. And what I mean by that is that time that your or third-party security team has dedicated to assess your system, your program, they won't spend that time chasing memory corruption or coding bugs. They can really, truly focus and analyze and dig really deep into architecture, microarchitecture, and find things that you otherwise wouldn't expect. And to prove that statement up, to back up that statement, we have one internal example where our offensive security researchers were able to dig very deep inside the architecture and even the RISC-V ISA itself, so that they were able to find a vulnerability inside the RISC-V spec. It is actually an ambiguity that turns into a vulnerability, as it makes glitch attacks very straightforward. This vulnerability was responsibly disclosed, of course. Their work presented at this year's DEF CON, the largest hacker conference in the world. And this is an example how now the whole community could benefit from such a work. The previous issue has a proper valid fix, of course, but glitch attacks are a general problem, as you can't really prevent attackers from doing whatever they want when they have physical access to a device. And dual core lockstep, although being a safety requirement, is also one very efficient fault injection countermeasure we have introduced, apart from other countermeasures we have. Essentially, you'd have two cores, a functional and one redundant core, and with same inputs, and in normal circumstances, you should have a matching output. But if there is a glitch attack ongoing on the functional core, the processor can be configured such that it just shuts down itself on a mismatch. This just raises the bar significantly for attackers, as they would need to glitch 2 cores simultaneously in order to be successful, and the 2-cycle delay even makes things even harder. Of course, it is, if you keep adding new redundant cores and have TCLS with 2 redundant cores, that will make things even harder, but with higher cost, of course. Security is never done, and there's no such thing as perfect security, that is clear. But we believe that by having formal guarantees and hardened hardware, that will force attackers to work much harder and with special resources in order to get a decent chance to compromise such a foundation. We tend to put more emphasis, as I said, on guarantees whenever possible, and add mitigations for things like physical attacks. For applications and feature-specific functionalities, we can apply different scrutiny to different applications, as our isolation story between partitions is solid. I think that RISC-V is definitely one, if not the one, then one of the best things that happened to our industry in decades. And combining RISC-V with better tools, I think we have a great chance to elevate the security posture of the whole industry. Thank you.
Excellent. So for the people online, get those questions into the virtual channel. We'll certainly take those. We do have a question I can start off with here, Marko. Can you please expand on your comment about using formal methods for verifying hardware? Specifically, how high level is the checking?
A little bit, yes. So Joe from our hardware team did a talk on more focusing on hardware. We do use, I think, Synopsys and Cadence tools for proving, they're formal tools for proving hardware correctness. There's just a couple things, some stuff from the RISC-V specification that we prove. For example, the PMP rules, if the like what happens on an exception and things like that. I don't have like a list of examples that I can point now.
I don't see anything else virtually in the room, or let's go to in the room. Yes.
Yeah, so I'm not really that familiar with Ada or Spark, but some of the reasons you cited were really similar to the things we hear about Rust. So how do you compare the two languages? And would Rust be also an alternative?
Yeah, so good question.
Yeah.
The question was, can you make a comparison between Ada and Rust? Because we hear both are relatively, secure for similar reasons you would have selected them. And so say a little bit more about how you selected Ada and what you think about Rust.
That's a great question. And so I'm not that familiar with Rust, but anyhow, and I wasn't at all familiar with Spark since 2 years ago. But in general, how I see a progression, what I would like to see is to start adopting Rust more and more for the application software. I think for someone who is unfamiliar with both Rust and Ada, I actually think, including myself, that would be more comfortable with Rust than with Ada. But although you have memory safety if you use Rust, which is great, but you don't have these primitives. I don't think that Rust supports contracts, programming by contracts, which is a very powerful thing. And that level of formal guarantees you get with Spark, you just cannot get that with Rust. And also, I don't believe there is a safety certified compiler for Rust as well, which is showstopper for us, for example. So those are some high level difference, but I know that there are actually very nice comparison online that I read last year, I think. So definitely there are more details on that, I'm sure.
Yeah, that's a good segue to the next question that's online. I love questions that make me look smart, so this is one of them. Is NVIDIA developing an ISO 26262 certified compiler internally? Or is there a commercial product from a third party?
Ada Core provides that, yes.
It's the Ada Core product then?
Yes.
Okay. Excellent. Okay, next question here in the room. Yeah, so the question for the folks in the virtual conference is, can you tell us more about the isolation kernel, is that separation kernel? Are there plans to open source that, or is that going to remain proprietary and closed?
So this is, although we have shipped some versions are in production already with respect to NVRISCV separation kernel. This is still kind of ongoing effort, and we are still in progress with respect to transitioning from Falcon to RISC-V. So this introduces a lot of flux. I mean, there are a lot of changes that we are making on the go, so it is not, I anticipate a lot more changes in the future. So I believe that at some point we would definitely be looking into how to contribute more and what we can share. But currently it is very tied to our internal use cases. So at some point, maybe, I'm not sure.
Okay. Given that we're right near the end time, I'll look around and see if there's one more question. I don't see one online, but we have one here. Last question.
One easy question. Do you take advantage of RISC-V security modes, in particular supervisor and user mode?
Yes.
Yeah, so the question was, are you leveraging RISC-V supervisor and hypervisor modes in the design?
Yes. I mean, one of the biggest reasons why we adopted RISC-V was the privilege spec, which actually made us do a lot of checkpoints on the things that we wanted to have. So yes, we do have different cores with different privilege levels, but in general, in this example that I gave, we do have machine mode, supervisor mode, and user mode, and we have different kind of hardware access control primitives for separate for every single of these privilege modes.
Okay, let's thank Marko for his presentation, and we'll wrap it up. Thank you very much. Appreciate it. Nice
Thank
job,
you.
Marko.
Thank you very much.